picking back up where we left off, now we're going to get, this page kind of has some tricky examples. So we're going to get into some stuff that's going to be a little bit more complicated, and the reason why isn't really necessarily going to be the calculus. It's because of the extra algebra that we have coming up in these examples that we really didn't need to do before. Okay, so as a quick refresher, since it's been like a month since I made the last video, here's the formulas. I don't remember where I left off with that last video. But here's the formulas for your inverse trig integrations. When you see something that fits this formula, right, where the constant part is first and then you subtract the variable part, that will integrate into the sine inverse. And it's always u over a, right? Always u over a inside the argument. Technically, a secant needs the absolute value just to avoid any weird domain issues. But it's always u over a in the argument. Remember, the tangent and the secant inverses, they need the 1 over a. And then it's already assuming, right? See how it's all got du? It's already assuming we've already done the u sub. So if something kicks out from the u sub, it's assuming we've already done that. But here we would basically identify the a, and then for the tangent and the secant, we kick out the 1 over a. We identify the u, the variable piece. If you need to, kick out what needs to be kicked out because of the u sub. But then once you identify the two pieces and you figure out what, if anything, needs to be kicked out, then we just plug into the formula, we use the formula. But it has to fit this formula before we can use it. Like, it has to look like this before we could integrate into an inverse tan. Or it has to look like this. And remember, the u's must match. So sometimes we have to be creative. Whatever this one is, right, that one's not going to lie. We have to make that one match. And if that means putting in a number on the bottom, you put in that number on the top, that's okay. You make the u's match, then you keep it balanced. Then you check what if anything, kicks out because of the u sub. But it has to fit one of these three formulas to end up integrating into an inverse trig. If for some reason it's negative, right? If you had a negative, typically what you would do is you would just take the negative, you'd factor it out, and so you would integrate while it's positive, and if you integrate while it's positive, you would get to the tan inverse, and then you could just bring the negative back. Same thing with the negative. If you saw one here or here, it's more common to integrate into a negative sine inverse or negative tan inverse or negative secant inverse than it would be to correspondingly do your cotan inverse instead. It's like there's some debate. It's not really wrong. If you had the negative, integrating it into the cotan, it's not really wrong, because if you were to take the derivative of this versus the derivative of that, you would get the same thing. But technically, when we're doing these inverse trig integrations, you'd always want to integrate into either a sine or a tangent or a secant inverse. If you had something that was negative, while you could integrate it into the cotan, it's just more proper to take the negative out, work with the positive stuff, and then just bring the negative back. Right? So that's just a little note. Tangent inverse, sine inverse, and secant inverse. Those are the only trig functions you should be integrating into. If you start off with the negative, just factor out the negative, work with the positives, and then just bring that negative back at the end. Okay, so let's go through and let's do this page of notes. And these are going to be probably about as tricky as some integrals as we're going to get in Calculus 1 or Calculus AB. Let's look at them. Here we go. First one, it says I've got the integration of 1 over x squared minus 4x plus 7, and of course dx. Okay, so we've got this integration, and I'm noticing, okay, that doesn't really look like any of my three formulas that we just saw, right? It doesn't fit any of those three formulas. We're going to be done with the negatives for now, right? So it doesn't really fit any of those three formulas, right? I don't have a constant plus some chunk squared, or I don't have a constant minus some chunk squared, or I don't have a some chunk squared minus a constant, right? We'd always want this to be what's called a perfect square, and here we don't have that. We could try to do u sub, but if I set all of this as u, then the derivative would be 2x minus 4. If I had a 2x minus 4, I could work with it, and I could do the whole question with u sub. Where if I had any scale multiple, any scale factor of 2x minus 4, like if I had an x minus 2, then the u sub would work, and it would kick out a 1/2. Like that would be okay. But since this is quadratic, you would need something linear in that numerator, and without it, the u substitution just will not come together. So instead, we're going to have to do something. It doesn't fit for a u sub. Neither will the next one or the time after, right? None of these ones on this page are going to work with u sub. So we're going to figure out how can we somehow force the inverse trig to end up working. How can I make this into one of those formulas? And the answer for doing that is an algebra technique called completing the square. So this shouldn't be anything new. You should have learned how to complete the square in Algebra 2. You should have also re-seen it in your pre-calc class. If you took me last year for calc, I guess most of y'all are in calc AB, so I guess you wouldn't have seen me last year. Unless you're in BC calculus, then you would have seen this last year with me in AB. But completing the square is going to enable us to do this. Let's do a quick recap of what it means to complete the square. Something like x squared plus 6x plus 9. That's what we would consider to be a perfect square trinomial. The reason why is because it would factor, so that one's going to factor x plus 3, aka it's going to factor x plus 3 squared. Okay, we don't typically ever write out that one if we can write it as the binomial squared. So this is what's called a perfect square trinomial, so that it could factor into a binomial squared. Now, it needed this to be a 9. Okay, if that 9 would have been anything else, it wouldn't have factored into the perfect square trinomial. It could have factored, like, let's say if, oh my gosh, if it would have started as a 5, well, then it would have still factored plus 5 plus 1. That's cool, but that wouldn't have been a perfect square because it's not a binomial squared. So what you could do is you could then take this thing, which is not a perfect square, and you could complete the square. That means you're going to fiddle with this constant, and you could complete the square in order that it's going to factor nicely. So what you would have to do, remember for your basic quadratics, you have ax squared plus bx plus c. What you're going to do is you're going to find the linear coefficient, the b value. You're going to take the b value and divide it by 2. We're trying to figure out what is this number supposed to be. What would be that number that completes the perfect square so that it factors nicely? You would take the linear coefficient, divide it by 2. By the way, that is always how it's going to factor. But you would take the b value, divide it by 2, and then you would square it. And this thing right here, whatever that number happens to be, this is the number that's supposed to complete that perfect square. That's the number, b over 2 squared, that's the number that's supposed to be. And then if you had that number, it would factor really nicely and you would have the perfect square. If it's not there, you can go through this process of completing the square. So here, let's say we had something like this, x squared plus the 6x plus 5. If I wanted to complete the square, I know my b value is 6. 6 divided by 2 is 3. 3 squared is 9. Okay, so I know that is supposed to be a 9. So what you could do is just a little bit of witchcraft. Now, it depends on if you're working with an equation. If you're working on both sides of the equation, what you could do is you could add 4. And the reason why I'd add 4 is because now on this side, I've got the 9. But if I add 4 on the left, I would also have to add 4 on the right, right? If I put this in and I put that in, overall, I'm not changing the equation because I'm adding 0 as a net change. If I add 4 to the left and I add 4 to the right, my net change overall is that I added 0. Or if you wanted to, you could add 4 on the left, and then you could also subtract 4 on the left. If you add 4 and subtract 4 on the same side, the net change is again adding 0. So you can either add and subtract the same number to both sides, or to one side, or you could add or subtract the same thing from both. As long as your net change is 0, right? Multiplying by 1 and adding 0, those are the only two things we know right now that don't change the value of the expression. So I would put the plus 4 in because that's going to complete the square. And so now I would have that perfect square trinomial, and then you have some collateral damage over there. That's okay, but you would have this chunk, which would then factor really nicely. And again, the b over 2, this number right here, is always how it will factor. So you find the linear coefficient, divide it by 2, you square it. That's the number that's supposed to be there. And then you could kind of make that equation come into fruition by completing the square. So let's look at this one. Now, what you would always need to do, right, if your if your quadratic coefficient, if it's not a positive 1, then you'd have some work to do. We're pretty much not going to see that super complicated stuff in this class, but you would always need the quadratic coefficient to be a positive 1. If not, you would have to factor out whatever you need to factor it out to make it a positive 1 before you can then go through and finish completing square. Let's look at this first example. And let's go for it. Here I've got x squared minus 4x plus 7. Now that 7 isn't the correct number. This does not factor into a perfect binomial square. Like, that is not the perfect square trinomial. So what we're going to do is complete the square. Okay, now what you would do is just kind of work with the variable parts first. So go ahead, x squared minus 4x, and I'm just going to kind of move that 7 over a little bit, right? I'm just kind of breaking it up. What you're going to do is just complete the square with just the variable parts. The extra constant, that's going to end up kind of being some collateral damage, and we'll deal with it in a little bit. But I'm going to complete the square with just the variable terms. And so this is what I'm going to end up creating the perfect square in, and I just have to complete it by figuring out what number needs to be there and by putting it in or somehow creating it. Okay, so let's think about it. I've got x squared minus 4. The linear coefficient is minus 4. If I take that and I divide it by 2, I would get negative 2. Then I would take that and I would square it, and I know, hey, that's a plus 4. The plus 4 is the number that's supposed to be there in order to complete the square. Now, if I add 4, I'm going to keep it balanced by also subtracting 4. You don't really have an equation here, right? Since everything's just one expression, if I add 4, keep it balanced by also subtracting 4. So putting this number in is what completed the square. That's going to be x minus 2, aka that's going to be x minus 2 squared, right? That's the perfect square trinomial. That factors really nicely. And then over here was just your collateral damage. We had the that number that we started with, and then with the minus 4 was the balancing act. And so here I'm going to end up with this. I'm going to end up with the integration. You have dx, and instead of this on the bottom, I'm going to have x minus 2 squared plus 3, right? And now that is going to end up fitting one of your inverse trig formulas. Now, we knew just from the looking at it at the beginning of this question, since there's no square root, I know the only option that it could have potentially been is an inverse tan formula. But I needed to fit this formula first, where I have a perfect square, and the number, we kind of like it when it's a perfect square like 16 or like 81. It doesn't have to be, right? We can always take the square root of a number even if it's ugly, but we needed the variable part to be a perfect square, and the order doesn't matter for how you write them. So now this one will fit an inverse tan. Awesome. The a value, it's not 3. The a value is the root of 3, gross. And then the u value here is x minus 2. And if u is x minus 2, you don't really have to worry about u sub because the derivative of that piece is just 1, so you're good to go. So now that I have completed the square, now I can know that this is going to integrate. It's going to be an inverse tangent. It's going to be u over a, so x minus 2 over the root of 3. Don't worry about rationalizing. Of course, we have the plus c. I shouldn't have used so much space for that other example. And then don't forget the inverse tan needs the 1 over a. So 1 over the root of 3 again. You don't have to worry about by rationalizing the denominator. I don't care. So here we'd end up getting 1 over the root of 3, tan inverse, x minus 2 over the root of 3, plus c. You had to complete the square first. You had to do some algebra before it would fit that inverse tan formula. And so, yeah, it's a little bit harder, but we should be able to do algebra. Okay, let's move it on to the next one, which is also not going to fit something, right? If I had, let's see, the derivative of this chunk, if I was trying to do a u sub, if I said all of this is u, the derivative would be a negative 2x plus 6. If I had a negative 2x plus 6 on the top, life would be good, right? And u sub would work. Or if I had any scale factor of it, if I had a minus x plus 3, that would work. Any scale factor, positive or negative, but any scale factor of minus 2x plus 6 would work for a u sub if I had that in the numerator. I don't have anything in the numerator, so u sub's not going to work. At least not for the whole thing. There's going to be a u sub within the inverse trig, but u sub doesn't get the whole question accomplished. Now, this doesn't fit anything at the beginning, so we're going to have to complete the square. Now, the first thing you would need to do, that coefficient is not a positive 1. So the first thing you would need to do is factor out that negative. Even if you had a number like a plus 4, you wouldn't care. You would only complete the square with the variable pieces. So you'd only be factoring out the negative from the variable pieces. Whatever that extra constant is, you kind of just move it off to the side. You only complete the square with the variable chunks at the beginning. But I need to factor out that negative first to make it a positive 1x squared. That means here I'm going to have a minus 6x, right? And then I can complete the square. But if the coefficient is not a positive 1, you would need to factor out whatever you have to in order to make it positive 1. If that was a 2, if that was a negative 2, then you would have had to factor out the negative and the 2, and then I would have 1x minus 3. Okay, whatever you have to do to to factor out and get the quadratic piece as a positive 1 coefficient, you'd have to factor out that same thing from all of the variable chunks, right? All 2 of them. Here I just had to factor out the negative. If you had to factor out a constant also, so be it, but we didn't have to. All right, -6 divided by 2, that's -3. -3 squared is 9, right? +9. So +9, that's the number that would create that perfect square trinomial. And this is all going to factor. It's x minus 3, right? The b over 2 is how it factors. So it's going to factor x minus 3 squared. Don't forget the negative out in front. So let's think about keeping this thing balanced, because I can't just put this 9 in. That's changing the value of my expression. What I would have to do is I'd have to make sure I keep that thing balanced. And now here's the thing that students are going to be prone to doing. You're going to be like, Mr. Bell, I put a +9. To counterbalance a +9, I'm going to -9. I'm like, oh, thanks for playing. You're so close. But then you dropped the ball. You didn't score, right? Okay, you messed it up. It really looks like that's a +9. But remember, you're adding 9 inside these parentheses, and everything inside the parentheses is negative. So even though that visually looks like you're adding 9, you're really subtracting 9. So since here putting this in meant I was subtracting 9, to counterbalance it, I would have to +9. I know that gets a little bit tricky. If I have to factor out a coefficient, whether it's a negative or whether it's a -2 or whatever, remember, whatever you put in there isn't exactly what you're doing to the equation, because that stuff out in front of the parentheses is affecting my term here. You'd have to think, what do I have out there? Multiply that by this, and then counterbalance to make sure we're keeping it all fair. Right, so here, once I complete the square, this is what I would end up having. I would have the integration of 1 over, you still have a square root, and then since that one's negative, I'm going to write 9 minus, so 9 minus x minus 3 squared. So completing the square, doing that algebra, now gives me this as my integration, where I know this isn't going to be a tan inverse because it's got a radical. I knew that from the get-go. And now I can also decide whether it's a sine inverse or a secant inverse. Since the constant comes first and the variable part is second, I know that this one's going to be a sine inverse. Right, so sine inverse, the u of this thing is going to end up being the variable chunk, x minus 3. Again, if u is x minus 3, the du would just be 1, so that's lovely. So we know which form it's going to be. We know nothing's going to kick out because of the u sub. Now the a value here is 3, so this one's going to be pretty nice. Okay. By the way, since this was a negative x squared, since you know you had to factor out that negative, right, that chunk ended up being negative, the fact that that was a negative x squared kind of told you that it was going to be a sine inverse, because the variable part is negative only for the sine inverse. The variable part would have been positive for both the secant inverse and the tangent inverse. So the fact that it was a negative, kind of this right here told you that was going to be a sine inverse. All right, so let's just put it all together then. So this is going to be sine inverse u over a, so x minus 3 over 3. And then sine inverse, we didn't need anything for the u sub, so that's great. And sine inverse does not need 1 over a, so then all I would need is the plus c, and then we're done. So we had to complete the square first, and then we could see how it ended up fitting one of those inverse trig formulas. Okay, hopefully those are all right, because it's about to get harder. Let's see, the next one, we have x plus 2 over the square root of 4 minus x. Okay, if that 2 wasn't here, u sub would work. Because if that 2 wasn't there, if the denominator has a 4 minus x squared, okay, the derivative would be a negative 2x. The fact that you're missing the negative 2 is okay, right? U sub could always kick out the negative 1/2 to account for it and explain why it's missing. But since this u would be quadratic, having the 1x on the top would work, right, for the u sub. But since I have this extra plus 2, that doesn't work. Right, so what we're going to do is a little bit of witchcraft. We're going to take this, and since the denominator is only one term, it's okay to split up this fraction. So here I'm going to split it up. I'm going to keep the x over the radical, and I'm keeping the x over the radical knowing that that piece is going to work with u sub. It's not going to work perfectly, but it'll work. And then we'll have plus, and I'm going to put 2 out in front, 4 minus x squared. If you want, you can put the 2 out in the front, or if you wanted to, you could put it up there on the top. It doesn't matter. I just like to factor it out. But here, we just took this thing and we split it up. We had x over the radical, and then the second piece we had plus 2 over the radical. I just factored out the 2. Now, this piece is going to work with u sub, right, where my u would be 4 minus x squared. The du would be a negative 2x dx. You have the x, you have the dx, you're missing the negative and the 2. That's okay. We know the u sub is just off by a negative 1/2. So that one's a negative 1/2. You got a square root on the bottom, so it'll be u to the negative 1/2 power. But that one will be done with just u sub. Okay, if you needed to write it as negative 1/2, 1 over the square root of u. If you need to do this step first and then get to there, that's okay. I just kind of skipped. Instead of having the square root on the bottom, right, all this was the negative 1/2 in the du. And then all the square on the bottom was the u to the negative 1/2 power. Okay, sorry, I had to talk to someone really quick. So anyways, let's get back to this example. The first part, we split it up. The first part ended up working with u sub. It was off by negative 1/2. That's okay. If you need to write it like this, right, go from this to this to this, then to this, that's okay. Or if you can just switch it all over in one step, that's all right. But now this is something that we could integrate, right? Now that's something that I could just use the power rule. If I add 1 to the exponent, divide by the new number, right? That one's going to be done. The 1/2 and the 2 are going to cancel. So I'm going to have negative stuff to the 1/2 power, or a negative square root of stuff either way. So here we're going to have negative square root of whatever that u chunk was. So that was 4 minus x squared. And now that part's all done. Right, the first integral, when you split it up, the first one was done all with the u sub, and now we would just have to do the other piece, which this piece, now that the variable is no longer in the top, now that this is just a constant, u sub has no business at all being in play, but now this is going to fit an inverse trig. So this one was u sub, but then this one is going to end up being an inverse, and since it's a constant minus the variable, that one's going to end up being an inverse sign. The u is just x. That's really lovely, because then nothing's going to kick out from the u sub within the inverse trig, and then the a here is 2. So all of this stuff, right? You have the 2. All of this stuff ends up integrating into your inverse sign u over a, so x over 2, and then plus c. You don't need a plus c for this piece and a plus c for this piece, right? We only need one plus c at the end. So then we finished that part. We've now done that part. So now we would just need to connect them. So we'd have plus 2 sine inverse of x over 2, and then again just the 1 plus c. And then that would be the answer for this. So that's a little tricky. U sub doesn't work for the whole thing, but if I split it up, U sub will work for part of it, and then the inverse trig works for the other part. Now the next one is going to be even harder. Okay, and I'm going to get out a piece of paper. Yeah, I'm just probably going to do this one on a piece of paper just to save the room. Doesn't matter. I'm going to throw away these notes packets in about 20 minutes anyway, so it doesn't matter. All right, here we go. We've got the 2x plus 5 over x to the x squared plus 8x plus 25. Okay, this looks almost really appealing to try with the u sub. Now, if I was going to do u sub, I would set the denominator as u, so I'd have x squared plus 8x plus 25. Okay, so then my derivative, du, would be 2x plus 8. Right, now in a perfect world, that is what I would have in the numerator. It's like, oh, so close. If only that was an 8 instead of a 5, then the whole thing would be a pretty easy integration. Now, it wasn't an 8, right? It was a 5, and we're going to have to deal with that fact. And how we deal with that, it's going to kind of be some witchcraft. All right, so let's think about this. 2x plus 5, that's the same thing as 2x plus 8, right? I'm creating the chunk that I want, but remember, we started with 5, so I'm going to have 2x plus 8 minus 3, right? 8 minus 3, that's the same thing. That's the same thing as my 5. But I'm specifically kind of targeting the 2x plus 8 so that I could now split this integral up. Right? So I'm taking the 5 that was there initially, and I'm splitting it up, and I'm rewriting it as 8 minus 3. And now what I'm going to do is I'm going to keep these things together, Why am I keeping those things together? Because that's what's going to fit the u sub. So I'm going to keep these over the denominator. And then the negative 3, well, that's just going to have to be a second piece. Okay, so I'm going to split this up. I have the 2x plus 8 over this denominator. And then I have a minus 3. I'm just going to write that as a coefficient. So minus 3. And then we have this denominator. Let's see. How can I keep this on? I'm just whatever. Okay, yellow. We're done. So now I'm going to take this. Let's see if I can keep it on the screen and write it over that same denominator. X squared plus 8x plus 25. So the u sub didn't work for the whole thing. It was close, but I wanted the 8. I had the 5. So instead, I kind of created the 8. I changed it to an 8. And then I kept it balanced, right? I just added in the 3, so I subtract the 3 to keep it balanced. But I'm creating this piece because I know when I split it up, this piece is going to work with u sub. Now, this piece is not going to work with u sub. This one's going to have to be an inverse trig, right? You could leave the 3 up here, or I think it's easier to just factor it out. It's going to be an inverse trig. Now, you'll have to complete the square, and then you'll see that it's going to be an inverse tan. I know that it's an inverse tan because there's no square root. Okay, so this one's a little bit tough, but I could kind of target it, right? I figure out what would work for the u sub. So I create the 8 on the top by rewriting the 5 as 8 minus 3. Then I'm keeping that chunk together because that piece will be done with u sub. And then the collateral damage, right, the minus 3, that was just keeping it balanced. That's just going to end up being part of the coefficient of this inverse tan. Okay, so here we go. This piece would be the u sub. Let's just knock this one done and get it out of the way. This piece, it'd be the same u sub that we did earlier, and the 2x plus 8, that would match perfectly. So that one would just be 1 over u du, which would integrate ln of u. We don't need the plus c. We'll just put the plus c all the way at the end. So that one's going to end up being ln of that ugly chunk, x squared plus 8x plus 25. Okay, so we split it up. Before I split it up, I had to do some finagling. I took the 5 and I rewrote it as 8 minus 3, and then I kept the 2x and the 8 because that piece would work with u sub. The minus 3, my counterbalance, that's just going to end up being part of the coefficient for the inverse tan. Now, I will need to complete the square for this before the inverse tan will work. So let's go do that scratch work also. Tons of scratch work on this question. I'm just kind of shooing the 25 over. I'm thinking, okay, here's the 8. Remember, I'm only going to complete the square with the variable part. It was a positive 1, so that's good. Don't have to factor anything out. 8 divided by 2 would be 4. 4 squared would be 16. So I'm going to put the 16 in, subtract 16 out to keep it balanced. Now I know that's going to factor x plus 4, aka it's going to factor x plus 4 squared. Remember, this divided by 2 is always how it's going to factor. And then I'm just going to kind of recombine all that stuff. 25 minus 16 would be 9. So once I've completed the square, now that second integral is 1 over x plus 4 squared plus 9. And now I can see how, yes, that will fit the inverse tan. The u for the inverse tan is going to be x plus 4. Since u is just the 1x, you don't have to worry about u sub, right? Nothing's going to kick out because of the u sub here because it was a 1x. That's great. The a for the inverse tan is not 9. The a is going to be 3. Okay, so now I could use my inverse tan formula to finish this part. Now, don't forget, we had this 3 coefficient that was already there. The inverse tan, you'd have the 1 over a, right? So I got that accounted for. I didn't need anything for the u sub. So I have the 1 over a inverse tan of u over a. So x plus 4 over 3. And then we'll put the plus c. And then look, the 3 and the 1/3 would end up canceling. And I'd have just minus your inverse tan of x plus 4 over 3 plus c. And there's the answer. Okay, that one is a tricky question, and there's a lot of really good math involved in it. U sub didn't work for the whole thing, but I could split it up so that U sub would work for part of it, and I have to be really intentional with how we split it up, right? Since I needed that to be a plus 8, because the derivative of that term would have been 2x plus 8. Since I needed that to be an 8, I'm intentional with how I took that 5 and I split it up so that I would get the 8, right? So that number wasn't the coincidence. We targeted the 8. Now the -3, that's just the collateral damage. That's just the keeping it balanced with respect to whatever it started as, right? It was a 5. I needed the 8, so I had to balance it with the -3. That ends up just being part of the coefficient. It ended up canceling really perfectly with the a value. That was a coincidence. But that kind of counterbalancing, you had to do this witchcraft, had to put this number in so that the u sub will work perfectly when you split it up, and then that counterbalance just ends up being part of the coefficient for the inverse tan. Now let's think about something. If this had been a little bit different, if this, instead of it having been a 2x plus 5, what if it was just a 1x plus 5 over the same denominator? Okay, well, what if it was just a 1x? Okay, well, we would have to think a little bit harder about that. I would still try to set the same u, and I would take the derivative, but then if my numerator had a 1x plus 5, I would need to figure out what scale factor would I need, right? The u sub's not going to match perfectly if it's a 1x. We liked that it was a 2x, we just didn't like the 5. But if it was a 1x, we'd have to account for it not being a 2x also. So we'd have to think about what scale factor the u sub would be off to make it into a 1x. So we would have still assigned the same u, we would have taken the derivative, but then I would have said, hey, that's what it's supposed to be. Since it's actually only a 1x, this would have to be divided by 2. That means this would have to be divided by 2. And then you would end up having a 1/2 du is equal to the 1x plus 4. We liked that it was a 2x, so I only had to work with that constant, take the 5 and make it an 8. If I also had to worry about reducing this 2 to a 1, right, if that's off by a factor of 1/2, well then that would also have to be off by a factor of 1/2. So then I would have needed to do witchcraft, and I would have needed to create a 4. So then I would have had something like this. I would have had just the 1x plus 4. Now I started with 5, so then I would need plus 4 plus 1. Remember, all of that right there is your 5. All of that is your 5. But if I had the 1x, I wouldn't split it up to have a 2x plus 8. If I only had the 1x, I wouldn't want plus 8. I would only want the x plus 4. And then you would go through and you do the same process. But you would split it up so that this would have the 1x plus 4, but your u sub would end up being off by a 1/2. Or I guess when we do the u sub, the 1/2 would come up here. Okay, so if it had not been a 2x, if it had only been a 1x, you could still get it done. It would just be a little bit harder, right? Instead of it being a 2x plus 8, we would have needed a 1x plus 4, which means that this would have just been a plus 1, right? The balance would have been a plus 1 instead of a -3. So then this would have been plus 1. That would have just been plus 1. I'm going to stop writing the 1. So then the coefficient still would have ended up as plus 1/3. And then this would have been a 1/2, and that would have been a 1/2. Like, it still would have been doable, and it would have been a whole lot of similar work. But if it had been a 1x instead of a 2x, that changes what the partner number would have to be. Remember, the 8 was the partner for the 2x. If I only had the 1x, you wouldn't need the 8. So you wouldn't rewrite it as 8 minus 3. If it was a 1x, you would need that to be a 4. So then you would do the witchcraft to take the 5 and split it up into 4 plus 1, which would affect a little bit of everything, right? That one's going to be the u sub, but it's off by the 1/2 constant. And then the counterbalance, the plus 1, that just ends up that just messes with the coefficient a little bit. Doesn't really change a whole lot. It just messes with that coefficient. Let's do just one more, just to kind of drive it home. What if, last one on this example, then I promise we'll be done. What if, instead of it being a 2x, or what if instead of it being a 1x, what if I had seen something, and what if it was like, let's do a 6x. And it's still the same denominator. So remember, it was supposed to be a 2x. That was nice because that's the derivative of the x squared. But if it was a 6x, well then, hey, like this would have been off by a scale factor of 3. So then we would also need the constant to be off by that scale factor of 3. So here's what we would have done, right? We would have still set it up the same. And so the derivative would have been 2x plus 8, right? If I had a 2x, the partner would be the 8. If I had the 1x, the partner would need to be a 4. Here, since I had, what did I have, a 6x? Since I had a 6x, right, since that's off by a factor of 3, that thing's also going to have to be off by that same factor of 3. So I would want a 6x plus 24. right? That's the thing that I would need if I had had a 6x instead. So I would have taken that integral, and instead of taking the 5 and splitting it up into 8 minus 3, or instead of doing 4 plus 1, I would have taken that and I would have had the 6x plus 24. I would have taken the 24 because I know that's what I need. And let's see, 24 minus 19 would be 5. So here is your 5. But you'd have to be intentional about how you split it up and then how you correspondingly keep it balanced. The 8 and the minus 3, that was nice, right? The 2x needed the 8. If it would have been a 1x, you would have needed the 4. So you would have taken the 5 and split it as 4 plus 1, which would have made the u sub off by 1/2 and would have changed what that coefficient ends up being. If it was a 6x, or if it was any other scale factor, right? This was kind of telling you what the scale factor is off by, which in turn will dictate what this number needs to be. Since that was off by a scale factor of 3, that would need to be 8 times 3. That would need to be a 24. So then you'd have to take your 5 and make somehow that 24 appear. So I could rewrite the 5 as 24 minus 19. And then you would have kept it. Let's see if I can fix it. So all this would have been 6x plus 24. Right, everything in the top would have been 6x plus 24. And then that 6x plus 24 would have fit, but your u sub would have been off not by 1/2. It would have been off by a scale factor of 3. So then I would have ended up having this first chunk would have been a 3 ln of stuff. It would work. It's just a little bit harder since it was off by that scale factor. Now, of course, when it was off by the scale factor of 3, that also changed my counterbalance. So over here, it would have been a minus 19, which means this would have been a minus 19, which means this would have been a minus 19, which means this. You would have had a minus 19 over 3, so you would have had a minus 19 thirds. Right, so whatever that number was, we liked it when it was the 2x because at least it wasn't off by a scale factor, right? It matched perfectly. But whatever that scale factor is, even if that 2x is off, or if it's too small, a 1x, or if it's too big, like a 6x or a 4x, or any scale multiple of x, you would just have to kind of target and figure out, hey, whatever scale factor is off with my x, that same scale factor is going to have to be off by the constant. Then you would take that 5 and you would split it up to make that number appear. Whether you need that number to be the 24, or whether you need that number to be the 4, or whether you need it to be the 8, right? You just kind of figure out what number is supposed to be there so that the first part works with u sub, and if it's off by a constant, so be it. But you have to be very targeted and very kind of thoughtful and specific with how you split it up, how I do this little witchcraft to split it up so that the first part will work with u sub, and then the counterbalance, whether it was the minus 3 or the plus 1 or the minus 19, that just ends up being part of the coefficient. So the counterbalance part doesn't really matter because the inverse tan stuff ends up being the same either way. But whether it's off by a constant or not will affect the coefficient of the ln and the coefficient of that inverse tan. So that affects kind of how you would kind of targetedly split up that initial integral. Right? So that's a hard question. Even the way that it was, even with it being a 2x, which is nice because at least that matches, and I know it's not off by an extra scale factor. If it would have been off by a scale factor, right, off by 1/2 or off by a factor of 3, it would still work. It would just be harder. But even as it was not off by that scale factor, it was still plenty difficult. Okay, but hopefully that makes sense. You don't typically see stuff like that. You had to figure out how would the u sub work. You had to split up the integral. Part of it worked with u sub. The other part you had to do the inverse tan. You had to complete the square before you could do the inverse tan. There's a lot going on in that question. But I hope you guys were able to follow. Right? That was a good little question. Alrighty, let's do this last one, and then we'll kind of just. I may just skip the last page. I don't know. We'll do this one really quick, and then we'll decide. All right, let me put up this other pen. Don't need it anymore. Okay, it's already 38 minutes, so I think I'll probably just skip the next page. All right, here we go. We've got the integration of arc cosine. That's cosine inverse. And I've got on the bottom, I've got the square root of 1 minus x squared. This is something like we saw with natural logs, how if you had something like ln of x to the 4th over x, sometimes it's just easier to rewrite it. You have the ln of x to the 4th, and instead of having the x on the bottom, you could have the 1 over x. And you're like, okay, there's the u. There's the du, and it matches perfectly, right? Because the derivative of natural log puts that x on the bottom, right? So the reason why that's there is because the ln puts it on the bottom. Same kind of thing is true here, right? So I'm going to rewrite it. I still have this same integration. I'm going to write cosine inverse of x, right? That's this part. But then instead of having this square root on the bottom, I'm going to write 1 over the square root of that stuff on the side. And now hopefully that helps you see that the u sub will work. Here's the u. There's the du. It doesn't match perfectly, right? That 1 over the square root of 1 minus x squared, that is the derivative of sine inverse. So if I set the u as cosine inverse, the derivative would be 1 over the square root of 1 minus x squared. Remember, it would be the same thing as a sine inverse, except it's supposed to be negative. So this doesn't perfectly match the derivative, but all that it's off by is the negative. Right, so this would be negative squiggle to squiggle of u du. Right, and that's it. Why is all this stuff on the bottom? Well, because the derivative of a cosine inverse would put that stuff on the bottom. It's off by a negative, but that's okay. All right, so here we would have it. Then we could integrate it. We'd have a 1/2 u squared, and then we would evaluate it. So I'm going to have a negative 1/2, and then I have cosine inverse of x. And then that's going to have to be squared. Then we evaluate it. I'm still on the screen. Oh, there we go. From 0 to root 2 over 2. So I'd have a negative 1/2. Then I'd do the cosine inverse of root 2 over 2. Squared minus negative, so plus 1/2. Cosine inverse of 0 squared. And then we'd have to go to our unit circle. And we would figure out, okay, the cosine is root 2 over 2. There's 2 angles where that happens, but because of the domain restriction, we don't care about that one. We got the pi over 4. So this is pi over 4. So I'm going to have pi squared over 16. 16 times 2 is 32. So I'm going to have a negative pi squared over 32. And then here, plus 1/2, I need the cosine inverse of 0. Where is the x value 0? Well, that's going to be at the top of the unit circle. It'll be at the bottom too, but you wouldn't care about that one. So that's going to be pi over 2. So this is pi over 2 squared, right? Here we had it squared, right? There it was pi over 4. You would still need to square it. So we had pi squared over 16. Then the 16 and the 2 gave us the 32. This is also, we have a 1 and a pi squared on the top. So that one's going to be pi squared. 2 times 2 is 4. 4 times 2 is 8. So that would be pi squared over 8. So you could write it like this. And there's nothing really wrong with that. If you wanted to combine it, right, let's see, I would need a common denominator, and the least common multiple would be 32. So this would be the same thing as 4 over 32. And if you have a negative 1 and a positive 4, those are like terms, so you could combine them. This would end up being 3 pi squared over 32. That's like a pretty horrendous looking answer. You could have left it as the negative pi squared over 30 plus the pi squared over 8. But if you wanted to combine it to one final singular answer, you could have. Okay, let's just quickly look at this next page. This next page is just a review, right? This is some old questions. I'm not going to do them. All of them should be review. Okay, so you really shouldn't need to watch a video of me going through those notes. If you do, really should just go back and watch previous videos. I'll show the answers, so if you're curious, you can pause the videos and then you can kind of look through them at your leisure. I'm not going to work through them just because I don't want to, and this video is already long. First one would be a u sub, it's off by 1/3. That one would be a u sub, it's off by a 1/5. Right? That one would be a u sub. You set the u as tangent of 2x, so it's going to be off by 1/2. But the derivative of tangent is secant squared, so that secant squared is not a problem. Right? It's u to the 3rd power. There's all the du part, but of course it was missing the 2, so it's off by 1/2. So u subs, that's great. Really u sub for all three. And then the next one, you'd have, since the top is bigger than the bottom, you would need to do the division first. Once you do the division, then you could reduce it from the improper function into this more mixed function. After you've done the division, then you could integrate it. Something like this, again, would be u sub. If you need to, you could write the 1 over x on the side, but that one's just a u sub, as you can see it, and it's a definite integral, get the answer. And then the last one would also just be a u sub. So this page is really just a bunch of u sub questions, and then really you have the one where you have to do the division first. So that one's not u sub, but everything else is just a kind of collection of old stuff. I don't want to go through and work it out. Here, I'm going to scroll up one more time for you. If you need to pause the video so that you can copy these notes down and see what the answers are, go for it. But here are the first three. I guess first, yep, that's the first 3. Oh, I'm missing one. Oh my gosh, darn it. Okay, so there's the first 3. There we go. And then let's now do, there's the last 3. Can I get them all on one screen? Yep, kind of, except I just can't get them to be horizontal. If you need to, pause the video, take the notes going through those, but all those should be reviewed, so I'm not going to go through them. Hopefully just looking at the answers is enough. All right, thanks for watching. I know this stuff was tough. This page in the notes is not easy. Sometimes you have to figure out, complete the square, and then the inverse trig will work. Sometimes you have to split it up, and then one part's u sub, the other part's inverse trig. Sometimes you have to split it up and be very specific with how you split it up, and then the u sub will work. Then you have to complete the square, and then the inverse trig will work. Some of those get really complicated, but I hope this video helped a little bit.